Okay, hello, welcome back. So now let's take a look at a particular condition in rectilinear motion, and that is motion with constant acceleration. So if you look at this cartoon, I have the particle moving along a straight line, and the acceleration in any direction, it could be either in positive or negative direction, is constant. And what we want to do is figure out how much s, the position, is changing as a function of time, and how velocity is changing as a function of time. So we want to fully find or solve the motion. But before I do that, maybe it's a good idea to reflect on what kind of situations may give rise to constant acceleration. A good example, the most common example, is an object falling through the gravitational field of the Earth. The gravitational field is almost constant near the surface of the Earth, and the object falling follows a straight path down, and that is a constant acceleration. Another good example is when you have an electric field and a charged particle. Well, maybe this is, yeah, that's good. It is good. Let me draw it like this, a little bigger. You have this constant electrical field between two charged surfaces. You have a particle here, and the particle moves along the electrical field with constant acceleration. That is also a good example, and it shows up a lot, for instance, in particle accelerator, when you have these constant electrical fields within the loops. What else? What other example? Oh, sometimes you can actually artificially create motions with constant acceleration because you want to. An example is in robotics, when you design a robot to follow a certain trajectory, a certain path, the starting and ending of the motion is usually a constant acceleration phase until the robot reaches its desired speed and follows the path with that speed. So beginning and end is sometimes, not always, but usually, is a constant acceleration motion. So another one, let me draw a cartoon. A robot like this moving. Okay, going back to our equations. So I know acceleration is constant. A equals, let's call it AC to emphasize it is constant. Now we saw that velocity, v, at any time, let's call it v, equals v at initial time plus integral from t equals 0 to t of AC dt. And AC is a constant value, so it can come out of the integral. I have v naught plus AC integral from 0 to t of just dt. And that this integral is just t. So that I have v naught plus ACT. So if I know the initial velocity, I know how much time has passed, I can calculate velocity as a function of time at any time in future. And let's go one step further. Let's look at positions. So I knew S is S naught at the beginning plus integral from 0 to t of v dt. Position is the integral of velocity. And I have the expression for velocity from up there, so I can write it down. I have S naught plus integral of 0 to t v naught plus at or act ACT dt. And this integral can be expanded as naught plus integral 0 to t v naught. No, actually, let's keep it as is. It's not too difficult of an integral. So it's a polynomial, v naught plus ACT. The integral becomes v naught t plus 1/2 ACT squared. The integral is from 0 to t. If you put the bounds of integral, if you put 0, everything becomes 0. And if you put t, you will only left with just the expression as is. So we have S naught plus V naught t plus 1/2 ACT squared. Similar as before, if you know the time, the constant acceleration, and initial velocity, and if you know where you were at the beginning, you can figure out where you are at some later time. So these are the constant acceleration. Let me write it this way. Solution to equation of motion. Let's do it this way. To equations of motion if acceleration is constant. So I emphasize this, acceleration is constant. I also want to emphasize solution. So these are not equations of motion, these are the solution to a particular case of equations of motion, and that case is when the acceleration is constant. Let's look at the final form of equation. Remember we had A ds equals V dv. And I can take integral because acceleration is constant. I have AC ds plus U equals integral of V dv. I'm taking these integrals between two states, so two time points or two states, because we don't have time here. This integral goes from some S naught to some final S. This integral goes from V naught to some final V. And again, because the integral on the left hand side, we're dealing with a constant acceleration, it comes out. I have AC times S minus S naught, that is the integral of ds, equals the other integral becomes 1/2. Let me write it a bit more clearly. AC of S, when we have integral from S naught to S, equals 1/2 V squared. This from V naught to V. And if you put the bounds of integral, now this becomes a little easier to see. AC S minus S naught equals 1/2 V squared minus V naught squared. And often it looks nicer to take this 1/2, bring it to here, and there you have it. You have a relationship between the initial and final positions and velocities if acceleration is constant and known. And yeah, okay, that is all I have. Yeah, I don't think there is anything else to talk about. Again, we can see a lot more examples in class. So I'll see you then.